Welcome back. In this video, we're going to interpret solubility curves. We're going to look at the effect of temperature and pressure on the solubility of solids and gases. And we're also going to use Henry's law to calculate the solubility of gases. When we talked about solubility, we discussed that the solubility is a number. It is the maximum amount of a solute that can dissolve in a given amount of solvent under a set of conditions, including the temperature and pressure. Up to now, we've looked at how intermolecular forces affect solubility. Now we're going to evaluate temperature and pressure. For gases being dissolved in a liquid, gas solubility is affected by pressure. However, pressure does not affect the solubility of liquids and solids. Now, why is this? Well, the amount of gas that's dissolved is proportional to the partial pressure of that gas above the solution. The reason for this is because when there's more gas particles, this means that there are more molecules that are hitting the surface of the liquid at any given moment. Therefore, there are more of them that can be dissolved. This allows us to use Henry's law. Henry's law allows us to quantify the solubility or the concentration of dissolved gas in a liquid solvent, typically water, based on the partial pressure of that gas. Henry's law constant, the letter K, depends on the identity of the solute and the solvent, as well as the temperature. If we were to plot the solubility of gases as a function of their partial pressure, we would see a straight line. The slope of that line is going to be dependent upon Henry's law constant. Notice here that the value of the solubility is a function of both pressure and, in this case, the identities of the gases. What you see there is that the heavier the gas is, in general, the more soluble it is. Heavier gases means more London dispersion forces, which means it dissolves better. Let's consider an example. If you have carbon dioxide dissolved in water, which is how you make soda, then what's done is to put a high amount of carbon dioxide into the bottle to pressurize it to a very high value. What this does, this means that you have a very high partial pressure of carbon dioxide. Therefore, you are able to dissolve a larger amount of carbon dioxide into the water. And we can see that when we release that pressure by opening up the bottle, that the high pressured contents are allowed to escape, and then the pressure of carbon dioxide dissolved in the water greatly decreases, as evidenced by the bubbles that are leaving the solution. If you were to leave that solution out on the counter for a while and let it get warm, we would see that even more gas molecules leave. For all gases, their solubility will decrease as the temperature of the solution increases. This is because you're giving the gas particles more energy. Higher kinetic energy means that they can more easily escape the solution. So for all gases, we see that their solubility is going to decrease as a function of their temperature. Now, for solids, we see that it's not quite as easy, not quite as cut and dry. Take a look at this graph, which plots the solubility of various salts as a function of temperature when they're dissolved in water. What do you notice? Well, you should notice that for some solids, their solubility is going to increase with temperature. However, for a couple of them, the cadmium and the cerium solids, those decrease with temperature. Now, not on this graph, there are actually some solids, when dissolved in water, have very odd behavior. This is the solubility of sodium sulfate as a function of temperature. We see that initially it increases and then it decreases and somewhat levels off. Now, the reasons for the various behavior of different ionic solids is more complex than what we're going to deal with in Chem 110. So for now, what you need to understand is that the general trend is for ionic solids, the solubility increases with increasing temperature. So let's practice this. let's say you've got 45 grams of potassium chlorate dissolved in 100 grams of water at 90 degrees Celsius. We take precautions to avoid water evaporation. If we then cool the solution to 30 degrees centigrade and no precipitate is observed, how would we classify this? Would it be unsaturated, saturated, or supersaturated? Pause the video and try and determine this. Welcome back. So in order to evaluate this, what you first want to do is check and see what is the solubility of potassium chlorate in 100 grams of water at 90 degrees. Potassium chlorate is right here. At 90 degrees, we can see that the solubility looks like just above 45, maybe 46, 47 grams per 100 grams of water. So when we initially dissolve at 90 degrees centigrade, we have an unsaturated solution. However, we take and we cool that solution down to 30 degrees. At 30 degrees, only 10 grams could be dissolved. However, since we formed no precipitate, that means all of the previously dissolved potassium chlorate is still dissolved, and our solution would be supersaturated. All right, let's try 2 more problems. If in this case, the mole fraction of oxygen in the atmosphere is 0.21. If the barometric pressure is 0.975 atmospheres, what's the concentration of oxygen in the water? We're given the solubility constant for oxygen in water at this temperature. So what does this involve? We're using Henry's law here. How do we know? Well, we're dissolving a gas in water, and we are told the pressure of the barometer, the total atmospheric pressure. We're also told the solubility constant. So Henry's law allows us to relate the solubility or concentration of oxygen to its partial pressure. However, if you were to just plug in the pressure that's given, you wouldn't be correct. So let's go through this step by step. We're given the solubility constant for this temperature. We need to solve for the partial pressure of oxygen though. The barometric pressure is the total pressure. Since partial pressure of oxygen is the mole fraction times the total, we can take and substitute in that relationship for the total pressure. So the concentration of oxygen, or the solubility of oxygen, is going to be equal to the total pressure times the mole fraction times Henry's law constant. That means then our solubility of oxygen at this specific temperature is 2.7 times 10 to the minus 4 molarity. All right, here's one last question. What would happen to the value of Henry's law constant for a particular gas if the temperature were to increase? I'd like for you to pause the video and try and think through this one on your own. Welcome back. So how can we evaluate this? Well, we know that for gases, they're less soluble at higher temperatures. If they're less soluble, then at a given partial pressure, we would expect the solubility to be lower. So the solubility of a gas is equal to the Henry's law constant times the partial pressure of that gas. If we're in this scenario, let's keep a fixed pressure, but if the solubility goes down, then that means the Henry's law constant would also have to have gone down. That's it for this video. Thanks for watching. Have a great day.